Welcome to this problem-solving session. Today, we will explore problem number 1026, maximum difference between node and ancestor. This is an intriguing challenge that tests your ability to traverse binary trees effectively while considering ancestor-descendant relationships. Let's dive in and analyze the problem step by step. The problem is to find the maximum absolute difference between the values of any node in a binary tree and one of its ancestors. In this context, a node A is considered an ancestor of another node B if B is a descendant of A. This includes situations where A and B are the same node. We're tasked with determining the largest possible value of A.val, B.val across all such ancestor-descendant pairs in the tree. The input to the problem is the root of the binary tree, where each node contains an integer value between -10 to the power of 5 and +10 to the power of 5. The output is a single integer representing the maximum absolute difference we can find in the tree. To clarify the problem, consider the first example. Here, we have a binary tree where the root node has a value of 8, and its left and right children are 3 and 10, respectively. The tree continues branching, with nodes like 1, 6, 14, and so on. The output for this example is 7. This result comes from the pair of nodes where 8 is the ancestor and 1 is the descendant. The absolute difference between their values is 8, 1, which equals 7. Other pairs, such as nodes 3 and 6 or nodes 10 and 14, yield smaller differences, so the maximum remains 7. In the second example, we have a more linear structure. The root node has a value of 1, and it has a single right child, which is 2, followed by another right child with a value of 0. The output here is 2. This is derived from the pair of nodes where 2 is the ancestor and 0 is the descendant. The absolute difference between their values is 2, 0, which equals 2. Other pairs, like 1 and 0 or 1 and 2, produce smaller differences. Meanwhile, in the third example, there is only one node in the tree, with a value of 4. Since no ancestor-descendant pairs exist in this case, the output is 0. Now, let's look at the constraints and edge cases. The tree can have between 2 and 5,000 nodes, and the values of the nodes can range from -10 to the power of 5 to +10 to the power of 5. For edge cases, if the tree contains only a single node, the output is 0 because no ancestor-descendant pairs exist. Additionally, the tree can include negative values, so our calculations must always consider the absolute difference. For large trees, our solution needs to be efficient to handle significant depth and avoid stack overflow or excessive computation time. Lastly, we need to ensure the solution correctly handles skewed trees, where all nodes may be aligned to one side, and the algorithm should still compute the maximum difference accurately. To tackle this problem, we first considered a brute force approach. The idea here is to traverse the entire tree and, for each node, compare it with all its ancestor nodes to calculate the absolute difference between their values. While this method is intuitive and straightforward to implement, it does come with significant trade-offs. Specifically, it requires us to store the full path from the root to each node, and for every node, we perform multiple comparisons with its ancestors. This leads to a time complexity of approximately n squared, which becomes inefficient for larger trees. Additionally, the space complexity is high due to the need to store paths. Although this approach is simple and easy to understand, it's clear that it doesn't scale well for larger inputs. Recognizing these limitations, we explored a more optimized solution using a recursive depth-first search, or DFS, approach. The optimized approach leverages a key insight: the maximum difference between a node and its ancestor can only rely on the extremum values, specifically, the minimum and maximum values, encountered along the path from the root to the current node. Using this insight, we can significantly reduce redundant calculations. During a depth-first traversal, we calculate the maximum potential difference at each node by comparing its value with the current minimum and maximum values seen so far. These extremum values are then updated to include the current node's value before recursively exploring its left and right children. By passing the updated minimum and maximum values as parameters, we avoid the need to explicitly store the entire path. This approach is far more efficient, as it processes each node exactly once, resulting in a time complexity of n. Additionally, the space complexity is reduced to h, where h is the height of the tree, because the recursion stack replaces the need to store paths. While this method may feel less intuitive at first, its efficiency and scalability make it an attractive solution for this problem. Ultimately, we selected the optimized recursive DFS approach for its efficiency and minimal space usage. By recognizing that the maximum difference depends only on the extremum ancestor values, namely, the minimum and maximum, this method avoids the inefficiencies of the brute force approach. The ability to track these extremum values dynamically during the traversal eliminates the need for redundant comparisons and guarantees that the solution scales well to larger trees. Two key observations solidify this strategy. First, the realization that we don't need the full path but only the extremum values to calculate the maximum difference. Second, DFS inherently provides a mechanism to track these values efficiently without extra storage. The aha moment came when we understood that comparing all ancestor-descendant pairs directly is unnecessary, tracking just the min and max along the path is sufficient. The recursive DFS approach strikes the right balance between clarity and performance, making it the optimal choice for solving this problem. To solve this problem, the goal is to find the maximum absolute difference between the values of any ancestor and descendant nodes in a binary tree. An ancestor is any node that lies above the current node in the tree, while a descendant is any node that lies below or is equal to the current node. The key to solving this problem is to approach it recursively. At each node, we calculate the maximum and minimum values in the subtree rooted at that node. Using these values, we can compute the maximum absolute difference for that node. To ensure that the parent nodes can make use of this information, we propagate the minimum and maximum values up the tree during the recursive process. This way, every node has access to the necessary data from its children. The recursion is implemented in a helper function, DFS, node, which returns the minimum and maximum values for the subtree rooted at node. If the node is none, meaning we've reached a leaf node's child, we return INF, since such nodes don't contribute to the calculation. Otherwise, we recursively compute the minimum and maximum values for the left and right subtrees, and use them to determine the current node's minimum and maximum values. Once we have the minimum and maximum values for the left and right subtrees, we use these to calculate the maximum absolute difference for the current node. Specifically, we update a global variable, max_diff, by considering the differences between the node's value and the propagated minimum and maximum values from both subtrees. This ensures that each node contributes to the overall maximum difference calculation. After updating the global maximum, the current node then returns its own subtree's minimum and maximum values, calculated as the minimum of the node's value and its children's minimums, and the maximum of the node's value and its children's maximums. This process continues recursively, starting at the root of the tree. We initialize max_diff to 0 at the beginning and ensure all nodes are visited during the traversal. There are also a couple of edge cases to handle. If the tree is empty, we simply return 0 since there are no nodes to compare. Similarly, if the tree contains only one node, the result is 0 because a single node cannot have any ancestors or descendants. The recursive nature of the algorithm allows us to traverse the binary tree efficiently while keeping track of the relevant values at each step. The tree is traversed using depth-first search, which is ideal for this problem because it allows us to compute the necessary values for each subtree before propagating them upwards. This avoids redundant calculations and ensures that each node has complete information about its subtree. The data structures we use include the binary tree itself as the input, a global variable max_diff to store the maximum difference found during the traversal, and tuples to represent the minimum and maximum values of each subtree. This design ensures that the algorithm is both memory efficient and easy to implement. The time complexity is O(n), where n is the number of nodes in the tree, since we visit each node exactly once. The space complexity is O(h), where h is the height of the tree, as this is the maximum memory required for the recursion stack. To implement this algorithm, we define the helper function DFS, node, within the main solution class. If the current node is none, the function returns float inf, indicating that no valid values exist for the subtree. For non-null nodes, the function first computes the minimum and maximum values for the left and right subtrees by making recursive calls to DFS. Using these results, the current node calculates its own subtree's minimum and maximum values, which include its own value. The global variable self.max_diff is then updated by comparing the absolute differences between the node's value and the propagated minimum and maximum values from its children. Finally, the function returns the current subtree's minimum and maximum values to the parent node. The recursion starts at the root of the tree, and once all nodes are processed, the value of self.max_diff contains the maximum absolute difference between any ancestor and descendant node in the tree. This value is returned as the final result. This implementation solves LeetCode problem number 1026, maximum difference between node and ancestor, using a depth-first search (DFS) approach. The goal is to determine the maximum absolute difference between any node and its ancestor in a binary tree. The max_ancestor_diff method begins by defining a recursive helper function DFS. This function takes a node, the current maximum value, and the current minimum value encountered along the path from the root to the current node. If the node is null, a leaf node's child, it returns the difference between the current maximum and minimum values, which represents the maximum difference for that path. The recursive function updates the maximum and minimum values for the current path by comparing them with the value of the current node. It then recursively explores the left and right subtrees, calculating the maximum difference for each subtree. The result for the current node is the maximum of the differences from the left and right subtrees. The base case handles an empty tree by returning 0, as there are no nodes to compare. For non-empty trees, the DFS begins at the root node, initializing both the maximum and minimum values to the root's value. This approach ensures that all paths in the tree are explored, and the maximum difference is calculated efficiently. The time complexity is O, n, where n is the number of nodes in the tree, because each node is visited once. The space complexity is O, h, where h is the height of the tree, due to the recursive call stack depth in the worst case of a skewed tree. Here, we define the max_ancestor_diff method, which calculates the maximum difference between a node and its ancestor in a binary tree. The solution uses a helper function, DFS, to traverse the tree recursively. The DFS function takes three parameters: the current node, the current maximum value, and the current minimum value along the path. At each step, we check if the current node is null. If it is, we return the difference between the current maximum and minimum values, as that represents the maximum difference for this path. Otherwise, we update the current maximum and minimum values by comparing the node's value with them. Once updated, we recursively calculate the differences for the left and right subtrees using the DFS function. Finally, the maximum of these two differences is returned, ensuring that we capture the largest difference found in either subtree. Next, we define the tree node class, which represents the structure of each node in the binary tree. Each node contains an integer value, val, and pointers to its left and right child nodes. The class provides three constructors: a default constructor, a constructor that initializes the node with a value, and another that initializes the node with a value along with its left and right child nodes. This structure allows us to represent the binary tree clearly, enabling traversal and computation of the maximum difference between a node and its ancestors. The goal of this problem is to calculate the maximum difference between a node and any of its ancestor nodes in a binary tree. The difference is given by the absolute value of the node's value minus the ancestor's value. For example, in the tree shown, we start at the root node with a value of 8 and explore the differences as we traverse the tree. Initially, we set the maximum and minimum values to the root node's value, which is 8. As we move to the left subtree, we encounter node 3. Here, we update our current maximum and minimum values to reflect this node's value and continue further into its children. This step-by-step traversal allows us to calculate the maximum difference at each node, ensuring we account for all paths in the tree. The process continues as we explore the leftmost path of the tree first, starting from node 3 and going to node 1. At node 1, we calculate the maximum difference since it is a leaf node. The current maximum remains 8, and the current minimum becomes 1. The difference here is 8 minus 1, which equals 7. We then backtrack to node 3 and proceed to its right child, node 6. For node 6, the current maximum remains 8, and the current minimum is updated to 3. We then explore node AXS children. For the left child, node 4, the current maximum is still 8, and the current minimum is 3, yielding a difference of 5 at this leaf node. Similarly, for the right child, node 7, the values remain the same, resulting in a difference of 5 as well. Node 6 returns the maximum of the differences from its children, which is 5. Finally, node 3 returns the maximum difference from its left and right subtrees, which is 7. Now we move to the right subtree of the root node, starting with node 10. Here, the current maximum is updated to 10, while the current minimum remains 8. Since node 10 is a leaf node, the difference is calculated as 10 minus 8, which equals 2. With the left and right subtrees of the root node processed, the root node returns the maximum difference from both sides. In this case, that value is 7, which becomes the final output. Next, let's consider another example where the tree is skewed to the right. Starting with node 1, we initialize the maximum and minimum values to 1 and move down its right subtree to node 2. At node 2, the maximum is updated to 2, and the minimum remains 1. Continuing further, we reach node 0 and then its left child, node -1. At node -1, we update the current maximum to 2, and the current minimum becomes -1. Since this is a leaf node, the difference is calculated as 2 minus -1, which equals 3. Node 0 then returns this value, and node 2 propagates it upward as the maximum difference in its subtree. Finally, the root node, 1, also returns this value as the overall maximum difference for the tree, which is 3. In the edge case of a tree with only one node, such as a tree where the root is 5, there are no ancestor relationships to compare. Therefore, the maximum difference is simply 0, as both the maximum and minimum values are equal to the single node's value. This completes our walkthrough of the solution, demonstrating how to handle both standard and edge cases efficiently. The time complexity of this solution is O(n), where n represents the number of nodes in the binary tree. This is because the function DFS performs a depth-first search traversal, visiting each node exactly once. For each node, the operations performed, such as updating current_max, current_min, and calculating the maximum between left and right subtree results, all take constant time. Therefore, since we're processing every node once and the operations per node are O(1), the overall time complexity becomes O(n). This holds true across all scenarios, whether the tree is balanced, skewed, or unbalanced, because the traversal always visits every node exactly once, ensuring the time complexity remains linear in all cases. The space complexity of the solution is O(h), where h corresponds to the height of the binary tree. This arises from the recursion stack used during the DFS traversal. The maximum depth of recursion is equal to the height of the tree. In the best case, where the tree is perfectly balanced, the height h is approximately log n, where n is the number of nodes. In the worst case, such as a completely skewed tree, the height h becomes n, as all nodes lie along a single path. Hence, the space complexity ranges from O log n in the best case to O(n) in the worst case. The memory usage primarily comes from the recursion stack, with each recursive call storing local variables like node, current_max, and current_min, which consume O(1) space per call. With a maximum of h recursive calls, the total stack space is O(h). Since no additional data structures are used, the overall auxiliary space is dominated by this recursion stack. When comparing this optimized solution to a brute force approach, the advantages become clear. A brute force method would involve explicitly comparing each node with all its ancestors, requiring multiple traversals of the tree for every single node. For time complexity, this means that for each node, traversing its ancestors could take up to O(h) time. With n nodes in the tree, the total time complexity would be O(n*h). In the worst-case scenario, such as a skewed tree, this becomes O(n²). The space complexity of the brute force method would still be O(h), as the recursion stack depth depends on the tree height. However, the optimized solution avoids these redundant ancestor comparisons by simply carrying the current maximum and minimum values down the tree during a single DFS traversal. This reduces the time complexity to O(n), while maintaining the same space complexity of O(h), making it significantly more efficient. The big O analysis of this solution can be justified mathematically. For time complexity, recall that in a DFS traversal, each node is visited exactly once. During each visit, constant time operations are performed, such as updating maximum and minimum values and comparing results. This means the total number of operations is directly proportional to the number of nodes, resulting in a time complexity of O(n). For space complexity, the primary factor is the recursion stack depth, which depends on the height of the tree, denoted as h. In the best case, h is approximately log n, and in the worst case, h equals n. Therefore, the space complexity is O(h). In conclusion, this optimized solution achieves a linear time complexity of O(n) and a space complexity of O(h), making it an efficient and scalable approach to solving this problem. When solving this problem, there are a few common mistakes that candidates often make. First, many rely on the brute force approach, which involves comparing all ancestor-descendant pairs in the tree. While this may work for smaller inputs, it becomes highly inefficient for larger trees, leading to time complexities of O(n squared, or worse. Instead, look for ways to optimize, such as leveraging post-order traversal or dynamic programming techniques to reduce redundant computations. Another frequent issue is misunderstanding the tree traversal order. For example, using pre-order traversal when post-order is more suitable for propagating values from children to parents can lead to incorrect or incomplete results. To address this, always tailor your traversal strategy to the specific requirements of the problem. Lastly, edge cases are often overlooked. These include scenarios like trees with only one node, skewed trees, or trees where all node values are identical. To ensure robustness, test your solution on these edge cases and verify that it handles them correctly. Another area where mistakes occur is in ignoring space complexity. Some candidates use excessive auxiliary data structures, such as storing all ancestors of a node in an array, which can lead to inefficient memory usage. Instead, aim to minimize space by using recursion or iterative traversal with stack-based approaches that have lower overhead. Additionally, variable management during recursion is critical. Overwriting global or shared variables can cause unintended side effects and lead to incorrect results. To avoid this, pass variables explicitly as function arguments or use helper functions to keep changes localized. Proper handling of recursion and space complexity not only makes your solution more efficient but also demonstrates a deeper understanding of algorithm design, which is highly valued in interviews. When approaching tree problems in interviews, there are several key insights to keep in mind. First, pattern recognition is crucial. Many tree problems, including this one, revolve around parent-child relationships and can be tackled effectively with divide-and-conquer strategies or dynamic programming on trees. Recognizing this can help you identify the optimal approach quickly. Additionally, selecting the right traversal strategy is vital. While pre-order or level-order traversal might work for other types of problems, ancestor-descendant relationships often benefit from post-order traversal, as it allows you to propagate values from child nodes to their parents efficiently. It's also important to understand and articulate the trade-offs in your solution. For instance, you might choose an approach that optimizes time complexity at the expense of higher space usage, or vice versa. Finally, always be proactive about addressing edge cases during interviews. This demonstrates thoroughness and helps you stand out as a thoughtful candidate. To deepen your understanding, it's helpful to explore related problems that utilize similar techniques. For instance, the binary tree maximum path sum problem, LeetCode 124, relies on recursion and divide-and-conquer strategies, much like this one. Another example is the lowest common ancestor of a binary tree problem, LeetCode 236, which also involves ancestor-descendant relationships and recursive traversal. The maximum difference between node and ancestor problem itself shares many of these concepts, focusing on efficiently handling ancestor-descendant relationships. Additionally, the diameter of binary tree problem, LeetCode 543, is another classic that uses divide-and-conquer techniques. Now, when comparing approaches, the brute force method has the advantage of being simple to implement and easy to debug, but its high time complexity makes it impractical for larger inputs. On the other hand, post-order traversal with recursion is more efficient and scalable, though it requires more effort to implement correctly. Finally, using dynamic programming on trees can optimize both time and space, but it requires careful planning to design and implement properly. Understanding these trade-offs will not only help you solve this problem but will also prepare you for similar challenges in the future. Great job completing this problem. We explored how to solve maximum difference between node and ancestor by focusing on recursion and understanding tree relationships. Remember, tree traversal techniques are vital for many coding interviews. Keep practicing, and don't forget to like, subscribe, and check out more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!